Good evening, everyone. So welcome to my YouTube channel, Math Curriculum. So today we are going to see fifth lecture on sequence. Today we'll see types of sequences. So types of sequences. Sequences are of three types. Sequences are of two types: convergent sequence, and divergent sequence. Okay. Now, divergent sequences are of three types. Diverges to plus infinity. Second type is diverges to minus infinity, and oscillatory sequences. So sequences diverges to plus infinity. So we have three types of divergent sequences. I am writing it again. Sequences diverges to plus infinity. Sequences diverges to minus infinity. Okay. And oscillatory sequences. Okay. And oscillatory sequences. Now, oscillatory sequences are of two types. Bounded oscillates finitely and oscillates infinitely. Sequences oscillates finitely. Sequences oscillates finitely, and sequence oscillates infinitely. Okay. Now, so again I am recalling, sequences are of two types: convergent sequence and divergent sequence. Divergent sequence has three types: sequence diverges to plus infinity, sequence diverges to minus infinity, and oscillatory sequences, the sequence which oscillates. And oscillatory sequences are two types: sequences oscillate finitely, sequence oscillates infinitely. Okay. Now we will study each type of sequence and its subsequences. We will study each type of sequences and their subtypes in detail. So we start with convergent sequence. What is convergent sequence first? So we start with first type, convergent sequence. So let A and let A and be a sequence. Then AN is said to be convergent if there exists if there exists L belongs to R satisfying the following statement. What is that statement? Given epsilon greater than 0, there exists capital N belongs to natural number such that such that such that AN minus L is less than epsilon for all natural numbers greater than or equal to capital N. If this statement is true for some L real number, then sequence is said to be convergent. Okay? So there exists L belongs to S satisfying these conditions. You take any epsilon, there will be corresponding natural number capital N such that the difference of this term of AN is difference of term of sequence with L is less than epsilon if you are taking N value greater than or equal to capital N. Okay. So what is the meaning of this remark? So one thing I should write. In this case, we say that L is limit of this sequence limit of this sequence limit of this sequence an, okay, and we write it by limit of an is equal to L. We write like that. So remark, so if an is convergent, okay, so we also say that an converges to L, okay, and we write it an converges to L, or limit of an tends to L, okay. Now remark, now if an converges to L, then given epsilon greater than 0, there exists capital N belongs to N, such that an minus L less than epsilon for all N greater than capital N. So what is the meaning of this? We can write it okay. So this implies for L minus epsilon okay. So this okay. So convergence means all the terms of a sequence after certain stage will lie in this interval. So what is the meaning of this? It means that an converges to L, if and only given epsilon greater than 0, there exists capital N belongs to N, such that L minus epsilon less than an less than epsilon L plus epsilon for all N belongs to capital N. Again, what is the meaning of this in different language? We can say it that an belongs to this open interval for all and greater than capital N. Okay. Now, limit of the convergent sequence is unit. Result 1. Limit of a convergent sequence is unit. It means we have only one limit for convergent sequence. Okay, let A and be a convergent sequence. Let L1 and L2 are limits of An. Okay. Now, limit of An is equal to N. Is equal to N. This implies given epsilon greater than 0, there exists N1 belongs to N such that An minus L1 is less than epsilon by 2. Epsilon is greater than 0. We can take our new epsilon by 2. Epsilon by 2 will play role of new epsilon. This is epsilon by 2 is epsilon for me because epsilon is nothing but a real number, positive number. If we take its half, it is also a positive number. So we can take my new epsilon this and we can apply epsilon delta definition of convergent sequences. Epsilon definition of convergent sequence for all n greater than capital N. So let's take equation 1. Similarly, as limit n tending to infinity An is equal to L2, this implies G1 epsilon greater than 0, there exists capital N2 belongs to N such that An minus L2 is less than epsilon by 2 for all n greater than N2. This is equation 2. Now, put capital N equal to maximum of capital N1 and N2. Then we have from equation 1, what we have? We have this one, that An minus L1 is less than epsilon by 2 for all n greater than capital N. Okay, because capital N is greater than N1. So equation 1 will also hold for if we take n greater than capital N. And from 2 we have from 2. So this is equation number 3. Okay. An minus L2 less than epsilon by 2 4 or and greater than 4. Okay. So now from 3 and 4 we get, so I am taking L1 minus L2. So I can add An and subtract An and use triangle initiative. So what is this? This is less than epsilon by 2. This is also less than epsilon 4 or and greater than 4. So what does it mean? It means L1 minus L2 is less than epsilon because this is epsilon 4 or and greater than 4. Okay. So this implies 0 L1 minus L2 less than epsilon for any epsilon greater than 2. Now L1 minus and L2 are fixed. So this implies L1 minus L2 is fixed. So this implies their absolute value is fixed number with this property L1 minus L2 less than epsilon for all epsilon greater than 0. Now what is the meaning of this? Now what is the meaning of this? The meaning of this, because this is true for any epsilon. So we take epsilon as small as. So what does it mean? It is possible only when this quantity is 0, otherwise not possible. So this means inside thing will be 0. This implies L1. Therefore, limit of the convergent sequence is 1. Therefore, limit of a convergent sequence is 1. Okay. So this is true. Now, second result we are going to prove convergent sequences are bounded. Result prove convergent sequence is bounded. Okay. Let's see its proof. Let An be a bounded, be a convergent sequence be a convergent sequence Okay. Take epsilon is equal to 1, then since now by epsilon, Now since sequence is convergent, let's say an converges to L. Then given epsilon greater than 0, there exists capital N belongs to N such that an minus L less than epsilon for all N greater than capital. But what is the meaning of this? So using this, this will imply let's say it's 1. Let's say it's 1. Let's say it's 1. Now, I can write it an minus L plus L. Now use triangular identity an minus L plus L. Okay. So I can take epsilon is equal to 1. Taking epsilon is equal to 1, we get an minus L for all N greater. Now, an absolute value is equal to an. I can write it. I can add L and subtract L. So from 1, so this is less than from 1. So this implies an is less than 1 plus for all N greater than capital N. Let's say it's true. Now, take put K is equal to maximum of A first term, second term, up to an minus 1 term and this one. Okay. Then K is greater than equal to 0 and an is less than equal to capital K for all N belongs to N. So what is the meaning of this? Meaning of this is this sequence is bounded. So therefore, convergent sequences are bounded. Remark, bounded sequence need not to be convergent. You see this sequence, -1 to the power. This is a bounded sequence. Bounded sequence. Okay. Because this is a bounded sequence, but this sequence is not convergent. We will solve because if this sequence is convergent, then there exists L belongs to R satisfy G1 epsilon greater than, I am taking epsilon is equal to 1. There exists N belongs to N such that AN minus L less than 1 for all and capital N. Okay. Now it means we have this one. But if we take n odd natural numbers, okay. So there are two possibilities. There are three possibilities. There are three possibilities. Three possibilities. What are three possibilities? L can be positive, L can be negative, L can be 0, and L can be. So if L is less than 0, less than 0, then taking less than 0, then taking n even natural numbers we get. If we take even natural numbers here, so it will be positive 1. So it will be 1 minus L less than 1. But L is negative. So its minus will be positive. The inside thing is positive. 1 minus L. Note that because L is negative, so this implies minus L greater than 0. So if I will add 1 both these sides, it will be greater than 1. Okay. It means this implies this 1 minus L is greater than 1 and less than 1, which is not possible. Which is not possible. Which is not possible. Okay. 1 minus L can be greater than 1 and less than 1. This is not possible. Okay. So this implies L cannot be so L less than 0 is not possible. Now, if L is 0, then what will happen? Now, if L is 0, then what will happen? If L is 0, so minus 1, I am putting this 0 less than 1. So this is, so what is this then? This is 1. Not possible. So this implies, this implies L is equal to 0 is not possible. Now, if L greater than 0, then taking n odd natural numbers we get what we get. So if we are taking odd natural numbers minus 1 to the power n, it will be minus, and this is L. So this implies this is 1 plus L. So 1 plus L is always greater than 0 because L is positive, which is a contradiction. This is not possible. This is not possible. Okay. So neither possibility happens. Neither possibility happens, which is absurd, which is a contradiction to the fact that L belongs to R. So hence L is not convergent. hence this sequence is not convergent. Therefore, so we have find example where the sequence is bounded but not convergent. So bounded sequence will not be convergent. So there will be some sequences which are bounded and they will be convergent also, because convergent sequence is always bounded. Okay. Now I am going to see an example. If this sequence is this sequence convergent solution. Now this sequence is not bounded. This sequence is not bounded. So this implies this sequence is not convergent. Because convergent sequences are always bounded. If some sequence is not bounded, it cannot be convergent. Because every convergent sequence is bounded. If you can find that a sequence is not bounded, it cannot be convergent. Okay. So it is not bounded, so it is not convergent. Similarly, this sequence is not bounded, therefore it is not convergent. Now, example 2. Is this sequence convergent? So, I am trying to show that this limit tends to, this sequence is limit tending to 0. We can show that this sequence will be convergent. Okay. So I need to show it. Need to show it. So I will use epsilon definition of convergence. So what I will do that epsilon greater than 0. Now 1 minus n minus 0 is equal to 1, because this is a natural number. So I want to make it less than epsilon. So choose a natural number or fix a natural number. Fix a natural number capital N such that n is greater than 1 upon epsilon. Okay. This is giving the idea. Okay. I can solve it for n. 1 upon n. So if I roughly solve it, if I will roughly solve it, what does it mean? It will imply less than n. So my n should be greater than 1 upon epsilon. So I am fixing an epsilon. Ultimately, showing by epsilon, I need to find an n corresponding to epsilon. So I am choosing it. I am fixing a natural number first, that is greater than 1 upon epsilon. Now, then 1 minus n 0 is equal to 1 upon n. Okay, that is less than 1 upon n for all n greater than capital N. So this implies 1 minus n 0 is less than epsilon for all n greater than n. So this implies 1 upon n converges to 0. Okay. Hence, hence 1 upon sequence is convergent and limit of sequences, limit of this sequence is 0. Okay. Now we are going to see another example. Example 2 is this sequence 3 plus 2 under root n upon under root n convergent solution. So first you see this sequence 3 plus 2 under root n upon under root n. So you see this term of sequence. So if we can write this like this, that under root n will be cancelled out this. Now if n tending to infinity, this part will go 0 and limit will be 2. So we will show that this sequence converges to okay. Now, but we have to show it by epsilon definition. So what I will do? So I will subtract this from this sequence minus 2. Then it will be, after solving you will get it 3 upon. Okay. Now I want to make it less than epsilon. So what I will, rough idea I am using, solve for n. So I will solve for n. It will be, this will imply squaring both the sides. Now what I will do, I will fix the natural number first. Fix a n belongs to capital N such that capital N is greater than 9 upon epsilon square. Then 3 plus 2 under root n minus 2 is, that is 3 upon under root n. That will be less than 3 upon. Okay. That is less than epsilon for all. Okay. So what is the meaning of this? This means this sequence converges to hence 3 plus 2 under root n is convergent and limit of n tending to infinity 3 plus 2 under root n into n is equal to 4. Okay. So this sequence is convergent and the limit is 4. Whenever we ask for some sequence is convergent or not, if you guess, first you have to guess the limit if it is convergent, and you have to show by epsilon definition. Okay. So today's lecture was for convergent type of sequences, and we have discussed convergent sequence. We have shown that limit of convergent sequence is unique. Then we have shown that convergent sequences are bounded. We also show that bounded sequence may not be convergent, and we have given example, counter examples, and we have taken two examples to show that something is convergent, some sequence is convergent or not. So, and in both the cases, the sequence is convergent, and we have shown it by epsilon definition. Okay. So today's lecture up to this, if you have any comment related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you for next lecture.